Welcome back, students. Today we're going to be talking about the shapes of distributions. In order to begin talking about this, we're going to first remember what a histogram is. Now, a histogram is just a bar graph that shows the frequency data. Frequency is a measure of how often something occurs. All right, so these histograms showed how often a specific event occurred, the frequency of that event. Okay. Now, another thing to note is that the intervals that are going to happen here, you can look down at this table below to see an example of what an interval is, where we've got, it goes from this number to this number. So 1 to 8, that's the interval. Now, all the intervals need to be the same size. Okay, so to go from 1 to 8, we add a 7. To go from 9 to 16, we add a 7. 17 to 24, we added a 7. So every single one of those intervals is the exact same size, and that is important when you create your own frequency tables and histograms. Now, a histogram is another great display in order to show spread and distribution. Before, we've learned box and whisker plot, and that's what we've been using before. Today we're going to be focusing in on these histograms. Now, in order to make a histogram, first thing you want is a frequency table. That's what this is. It's just a table stating how often each event occurred. So we've got number of tickets sold, and so there were 5 times they sold between 1 and 8. There were 9 times where they sold between 9 and 16, and on and on and on. Or if these were individual sellers, perhaps there were 5 kids who sold this many tickets, 9 kids who sold this many, and on. But it's something along those lines. This problem is asking us to create or use the frequency table and display it with a histogram. And then we'll identify the shape. Now, the shapes are up here. And we'll talk a bit about those more after we get our histogram table made. First, histogram is going to come down like this. I want to make sure that the top of my histogram matches about my biggest number, which in this case is a 25. So I'm going to have this count by 5s. So there's 20, 15, 10, and 5. So good. Those are all approximately spaced out. Now I want to put in my intervals. The intervals go down at the bottom. So 1 through 8. 9 through 16, 17 through 24, 25 through 32, 33 through 40, 41 through 48, and 49 through 56. Okay, now all we need to do is put in our bars. So for the 1 through 8, it should be as high as 5. And there's our bar. For 9 through 16, almost up to 10, but not quite, so just there at 9. 17 through 24 should be up at 16, so just a little bit past the 15. 25 through 32 should be all the way up at 25, so right to the top. 33 through 40 would just be at the 20. 46 through 48, or 41 through 48, sorry, would be up at the 8. And 49 through 56, just barely below it at 7. All right. There is our histogram that we have made. Now, in order to identify the shape, we've got 3 shapes up here. We got skewed left, symmetric, and skewed right. Now it tells us here that skewed left has a tail that extends to the left. Notice how it starts flattening over here to the left and the peak is on the right. That's what we call skewed left. Skewed right does the exact opposite. It tails off towards the right and has the peak here in the left. Symmetric, the peak is about in the center. So our peak was about here in the center. We had 3 bars going lower to the right, or to the left. This has 3 bars going lower to the right. Both sides are approximately the same size. Now, they're not exactly, and that's important to note. It doesn't have to be exact to be symmetric. So long as it is approximately so. So long as approximately it's similar to the right and the left, that we would call it symmetric. Now, we discussed earlier that there are different times when we use different measures of center, okay? Speaking about mean, median, and mode. Now, at that time, we discussed why the mean is a bad measure of center when you've got outliers, because we just think of grades. One single bad grade drops everything. Even if you had been very consistently getting good scores, that one bad grade can drop everything drastically. Outliers move the mean a lot, and that can mean that the mean in the presence of an outlier isn't necessarily showing us what's normal, what's average. The same can be true of skewed data. So I want to direct your attention to these 2 graphs down here. Notice how the mean on left skewed is further to the left than the median is. And this is the very reason we call it skewed left. Our perception of what is normal is being skewed to the left because of the tail. The mean is being moved to the left because of the tail. With skewed right, the mean was being moved to the right because of the tail. The tail is operating in a very similar fashion to how an outlier did. A very small group of numbers is moving the mean more than perhaps is justified if what we care about is saying what's normal. Now, with symmetric data, the mean and the median are going to be approximately the same value. And in those situations, the mean is going to be a more valuable measure of center. So we use median when the data is skewed, and skewness damages our perception, so we don't use the mean. But when it's symmetric, we will use the mean. Okay, so with symmetric, like it says here, you use the mean. Along with that, we would use the standard deviation to describe the variation. When your data is skewed, that means we're going to be using the median and the 5-number summary. The 5-number summary are those data points that we use to create a box and whisker plot. Minimum, first quartile, median, third quartile, maximum. That's your 5-number summary. And you would use those and perhaps even a box and whisker plot to describe your variation. Okay, all right, so let's take a look at this data, and we're going to try to pick the appropriate measurement given this data. We got a police officer measures the speed in miles per hour of 30 motorists, shown to the right. First, we want to display this data in a histogram so that we can figure out, is the data skewed or not? If it is skewed, we'll choose certain measurements. If it's not skewed, we'll choose others. Now, it says we're going to have it do intervals of 31 through 35. So 31 through 35. Notice how it added 4. Next number up would be a 36. Add a 4 to make it 40. Then 41. Add a 4 and it goes to 45. Then 46, add a 4 and it goes to 50. And then 51, add a 4 and it goes to 55. 56, add a 4 and it goes to 60. And let's see, do we have anything above 60? Doesn't look like it. So I'm probably good there. Next thing I'm going to do is I want to get a good solid count of each of these. We'll finish up with the box and whisker plot. But in fact, before I finish up this histogram, I'm going to want to create a frequency table. All right, so here's my frequency table. I just got all my intervals right there. And what I'm going to do to start filling it in is counting how many numbers exist in each one. So for 31 through 35, let's see, we've got the 32. And that looks about it. So there was only one for 31 through 35. Then for 36 through 40, got a 38, a 40, 39. So I had 3 there. And I'm crossing them off as I go along so that if I miss one, I can make sure to add it to my count near the end. All right, so 41 through 45. A 45, a 44, a 41, a 45, 42. So 1, 2, 3, 4, 5. All right, and give me a second and I'll finish this up. All right, so I finished up my table. I even did make a few mistakes along the way, and having crossed them out as I went along made it easier to add them in again at the end. I notice my biggest number here is an 11, so I'm going to go ahead and make this go as high as a 15, which means we can separate it this way, that's a 10, and that's a 5, and we can make estimations for how high everything else is. So first, we've got 1, and 36 through 40 should be up at a 3. And then 41 through 45, up as high as the 5. 51 through 55, 46 through 50, up at the 6, so only just barely higher. 51 through 55, up at 11. 56 through 60 at 4. All right, so there's our data. Looks like we've got a very clear peak on the right. So it peaks over here on the right, and then it tails out over there. So this is skewed left. All right, so that's my answer to A, skewed left. B, which measures of center and variation would be best to be used? Well, if it's skewed, it told me right up here, median and 5-number summary. So for my B, I'm going to say the median and the 5-number summary. Next, the speed limit is 45 miles per hour. So that would be right up there, upper limit of that one. How would I interpret these results? I would say people speed is what my results are, is that it's only a very small group of people who would go under the speed limit, but the majority of our people are over the speed limit. Okay? All right. So let's look at this next one. In example 3, we are going to compare two different histograms to see what we can learn from this. So the chart title is text messaging, and we've got our first histogram, which says female students, and the second one is male students. And it looks like they're using emoticon messages. So we have a count of how many emoticon messages they send. So the problem states, emoticons are graphic symbols that represent facial expressions. They are used to convey a person's mood in a text message. The double histogram shows the distributions of emoticon messages sent by a group of female students and a group of male students during 1 week. Compare the distributions using their shapes and appropriate measures of center and variation. All right, so here is what I am kind of getting from this. First, let's talk about shape. I'm going to move that over a bit. So they asked us to compare the shape. And we'll talk about female students and the male students. So as far as shape is going, the female students, that has a nice symmetric look to it. Okay, whereas the male students, the peak is over here on the left and it tails off to the right. So that means that is going to be right skewed. The measure of center that I would use to compare them, for the female students, the measure of center I'm inclined to use is the mean. Now the mean, because it is symmetric, is going to be at about the center of the peak, of where things are peaking. So I might even say it might be around there. So around 29 or 30 text messages that have an emoticon in it. Okay, the median is what I would use because that is right skewed. Okay, now my median, and actually I'm going to make sure to write that. So let's say that's about 30 just by looking at it. The median for the males, it's going to be near the peak. It'll be ever so slightly in the direction of where the tail is. So I'm thinking it's somewhere between the 10 to 19 would be my best guess. I'm going to go on the lower end and say, right now I'm guessing at about 10. Okay, so that's how I would do my measures of center. Okay, and then for variation, what would I choose to measure the variation of these? For the females, I would use the standard deviation. That's going to be the most useful measurement to talk about their variation. And for the men, because it's skewed again, I'm going to choose the 5-number summary. Okay, and just looking at it, we can also see certain things about the variation. It does appear that we have more variation among the girls. We've got this wider range among female students, and they do seem to be more evenly distributed, whereas for the males, we do see them being clumped over to one side, and all of them tending to be to that side with a smaller range. And so the men have less variation within their texting habits. Okay, now many real-life data sets have distributions that are bell-shaped. What I mean by bell-shaped is this shape that you can see right here, that symmetric curve. We many times will call that the bell shape. You can imagine a little handle coming out of the top. There. It's a handheld bell. Okay, that's what we mean by bell-shaped. And they're approximately symmetrical about the mean. So a lot of data sets have that. In a future course, you're going to study this type of distribution in detail, okay? Especially in Secondary 3, you're going to really jump into how to use this graph that I'm showing right now. For now, these rules are going to help you see how valuable the standard deviation can be to measure variation. So first off, remember that this symbol sigma represents one standard deviation. X with a bar represents the mean. So 68% of all responses tend to lie within a single standard deviation. That would be this dark blue area. 68% of responses will fall in there, meaning that they're either from one standard deviation below or one standard deviation above. If we extend that further out to include that light blue section, now 95% of all of our responses we expect to be within there. Now part of why that's useful is we do consider anything outside of two standard deviations from the mean, we consider that to be unusual. Okay, and in fact, it's this exact comparison, these exact numbers that were used when statistics was still in its infancy to decide whether or not statistics could be used to prove whether or not certain men who were claiming to be psychic were actually psychic. So essentially they devised this test where men claiming to be psychic would have to guess what's on the other side of the card. And if you've got limited number of cards, such as let's say every single card has an A, B, or C on it, A, B, C, or D, we expect them to get it right 1/4 of the time. So there would be an average. The average, if they're just guessing, would have been 25%. But if they could get a certain number right, that they were this far away from the standard deviation, we're starting to think something unusual is happening here. And that was approximately the test that was devised. And that's where this rule largely comes from, is that initial test that was devised by this statistician to test whether or not we could prove if these men were psychic. Now what that also means, if this whole blue, dark blue section represents 68%, a single blue section just represents 34% of everybody. Okay, so also keep that in mind. We can figure out what each of those smaller sections are by understanding how big the larger sections are. Okay, all right, so in this final one, we're going to compare these two distributions. We're given the numbers for the men and women and a lot of the statistical numbers that have come out of the analysis. So we don't have the raw numbers, we've got the statistics. This table shows the results of a survey that asked men and women how many pairs of shoes they owned. So first it wants us to make a double box and whisker plot to represent the data, and then we'll describe each distribution. So double box and whisker plot, I'm going to need a number line. The smallest number from either, we got 2 and 5, so I'm going to go ahead and start this one at 0. Then the maximums, we have 17 and 24, so I'll get a maximum of 25. Since I'm counting all the way up to 25, let's go ahead and try and count by 5s. So 5, 10, 15, 20. That's approximately evenly spaced. We'll go with that. There we go. So now to create our box and whisker plots, let's go ahead and start with the men. We got a minimum at 2, maximum at 17, and then first quartile at 5, median at 7, third quartile at 10, and that's everything we need for the box and whisker plot. All right, so now for and let's go ahead and label that. All right, so now women, the minimum was at 5, the maximum at 24, first quartile at 5. No, first quartile for women should have been at 12. Median at 14. And third quartile at 17. All right, so now let's describe these shapes. Both of the whiskers on the women's chart look around the same side, so I'm going to say that looks to be symmetric. Whereas on the men's side, the upper whisker, the upper 25%, appears to be far larger than the left, so this seems to be skewed to the right. So men don't tend to be here in that upper range, but we do have a few there. So we've got a few, not necessarily outliers, but similar to that idea. They're very spread out, and there's not many of them as you start getting to those higher numbers. So this is skewed to the right. So compare the number of shoes owned by men to the number of shoes owned by women. And actually, before I answer that question, let's also look at something else, because I want to drive this point home. Let's look at the mean, because they calculated it for us. So the mean here was at 8. So the mean for the men, notice how it's to the right of where the median was, and that's because of that skewness to the right. However, with the women, because it was more symmetric, the mean was at about 14, which that's pretty much that's exactly where our median was. With symmetric, mean and median are going to be about the same. With skewed, the mean is going to be further in the direction of the skew. All right, so compare the number of shoes owned by men to the number of pairs owned by women. Putting it simply, women have more. Notice in every single section, in every single measurement, women were higher. In their minimum, they were higher. In their maximum, they were higher. Their middle 50%, their box, the entire box is higher than the men's entire box. Women have more shoes. That's the takeaway by just quickly looking at that. Okay, about how many women surveyed would expect to own between 10 and 18? Well, let's look at where 10 is. And 18 would probably be at around there. So notice the entirety of women's box is in there. We know this box to contain 2/4 or half of all women. So I'm going to give my approximation that I'm going to say approximately 55%. It's definitely over 50%. because that range of 10 to 18 includes the entire box. All right, so this has been talking about distributions and shapes. I hope this helps you in your own analyses. Good luck.